Hello everybody, the Science Dude here, and back to you with another video, and this one is on how to count isomers of a given compound. Now, counting isomers can be a little tricky, but in this video I'll give you the steps and methodology to make it seem like a fun puzzle. So let's begin. So there are like multiple steps involved counting isomers. The first step is to calculate the double bond equivalent. There's an equation for this. The second step is to look at your compound and atoms and see what are the possible functional groups. The third step is to actually draw the structural isomers. And the fourth step is to account for stereoisomers. And the most important step is to practice solving these problems to get good at them. So the double bond equivalent essentially tells you how many pi bonds or rings are in a given compound. So essentially the equation is the number of carbons plus 1 minus the number of hydrogens divided by 2 minus the number of halogens divided by 2 plus the number of nitrogens divided by 2. So essentially, let's take a look at an example here. So you have C6H10O, right? So you're going to plug the values in, 6 carbons plus 1 minus 10, that gives you 2. And essentially what this number tells you is that there could be either, there is a diene or like 2 alkenes, there is 2 rings, or there could be 1 ring and 1 double bond, or there could be 1 triple bond, because 1 triple bond contains 2 pi bonds. And if same thing C4H6 here, there's like C4, plug in the numbers and get 2. The next step is to identify the various functional groups in a given compound. So you first calculate the DBE, the bond equivalent, and then you identify the atoms in the compound. So you take a look at this C4H80 or O. The DBE is you plug in the numbers, you get 1. And then with this information, you gotta think what functional groups are possible with an oxygen atom. So you can have an alcohol, you can have an ether, you can have an aldehyde, ketone, or a ring. Now, if you're having an alcohol, right? There must be an alkene because the OH group functional group does not involve a double bond. Same with an ether. And then, but however, aldehydes and ketones have a CO double bond. And then also this furan ring has a ring in it. So you got to think of the functional groups that are compatible with your information. But you have to also memorize the functional groups in order to make a decision. So you have to know your alkanes, alkenes, and alkynes. The benzene ring is also an interesting one. Like if you have a double bond equivalence of 4 or higher, you can infer there's a benzene ring because there's 3 pi bonds and 1 ring. And then you have an amine, alcohols, and ethers, and thiols, and alkyl halide, aldehyde, ketones. So you want to memorize them. The next step is draw structural formulas, structural isomers. So essentially they're molecules with the same formula, but like a different connectivity of atoms. So we have like this long chain of butane, but then in structural isomers like isobutane, where like one of the carbons branches off the middle carbon. And then another example of these alcohols. I think 1, 2, 3, 4, 5, 6, hexanol, these isomers of hexanol. So yeah. And the last step is if you still practice, the last step is to identify any optical isomers. So if there's a double bond, you have to identify if there's like a cis or trans isomers. So in a trans isomer, there are like the various groups, like the same groups, are on different sides of the double bond, and in cis, they're on the same side. And then on chiral centers, right? You have to identify like whether certain carbons are chiral center or not. And to identify that is that you need to find a carbon that has 4 different groups attached to it. So like this carbon has a hydrogen group, a hydroxy group, a methyl, and a carboxylic acid group. And thus it can form a mirror image of itself and reverse its orientation in this one over here. So you have to take into account those things as well. So basically these are enantiomers. So let's do some practice problems. So the first one we can start is with we can calculate the isomer, not calculate, count isomers of this simple compound C5H12. So the first step is to use the double bond equivalency equation. So DBE equals the number of carbons plus 1 minus number of hydrogens minus number of halogens divided by 2 minus plus the number of nitrogens. Since there's 0, there's 0. However, this will equal to 6 minus 12 over 2. That'll give you 0. And with this, you can infer that there is no double bonds or rings. So we're only dealing alkanes. So we can start off with long branch, not like long carbon chain of 5. Maybe we can put one in the middle. So we can do this here. And also have a carbon chain like a 3. So then we can put here and here. So these are our 3 isomers. It's pretty simple. Some of you may think, why can't you put the metal substituent over here? Well, essentially these compounds are equal to each other, because if you flip it upside up and transverse it horizontally, like flip it horizontally, you'll get this compound. Essentially, it's the same compound but in a different orientation. So there are 3 isomers for this compound. Pretty simple. Moving on to a harder one. Let's try with heptane, C7H16. Try finding this on your own. I'll give you a hint if you want. So there are a total of 9 different isomers of this compound. Try to find them all. Pause the video. Okay, so the first step is to find the one that has a long chain of 7 carbons. So you have 1, 2, 3, 4, 5, 6, 7, right? Now you're going to find a long chain of 6 carbons. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Now where does the other methyl group go? You can put in the middle. If you put in the end, you're just going to create another carbon chain of 7. So then you can do the same thing with other ones. You can put it in the middle. And yeah. Well, if you do this one right here, right? If you put in the middle, you're essentially just creating this compound. It's just in a different orientation. So that doesn't work. So I think those are the ones with 6 carbon long chains. So we're going to go to 5. So 5 is just this. We can put it here. We can put it here. Another one is we can also put it here. Another one is what? So we got it. We can put it here. Another one. And then we can also put it here. So I think those are 1, 2. Yeah, right? And then when you have 4, 1, 2, 3, 4, you can put one here and then 1 there, right? Yeah, so I think those are 1, 2, 3, 4, 5, 6, 7, 8. Oh, I'm missing something. Yes. So I forgot to put one in the middle. So these are how you find it. Yeah. So that's a little harder one. Clear canvas. Let's top it up a notch. Let's try to find one with more atoms. So let's try to find isomers of this compound. C3H8O. Let's calculate the double bond equivalency. So DBE equals 3 plus 1, 8 over 2. That gives you 0. So there's no double bonds or rings in them. So then so then you take into account the functional groups that involve in an oxygen atom. These include an alcohol, ether, aldehyde, ketone, and then ester and carboxylic acid. So you have these options. However, since there is no double bond, you can cross at ester, carboxylic acid, aldehydes, and ketones. And the only groups that are present is alcohol and ether. So let's find out let's find out the isomers. So if we go to alcohol here, right? If we go to alcohol, right? So we have a 3-carbon chain. So we can put an alcohol on the side. You can also put an alcohol in the middle. If you were to have a 2-carbon chain, we have to account for extra carbon. But if you put it at the end, which is our only option, we'll of course create a 3-carbon chain. So that doesn't work. So those are our 2 alcohols. And then our ether, we create a 3-carbon chain, but you have to cleave one part and add an oxygen atom. So that's 1, 2, and 3. So these are 3 isomers, or C3H8. Oh. Alright, so yeah. Moving on, let's go to a more difficult one. So we have C5H11Cl. Let's calculate double bond equivalency again. Equivalent. So we have DBE equals 5 plus 1 minus 11 over 2 minus 1 over 2. And that'll give you 6 minus 12 over 2, 6 minus 6 equals 0. So there is no double bonds or rings. So let's start again. So, and keep in mind that like alkyl halides, the halogen is on the terminal, is in terminal, because if it were in the middle of the carbon like an ether, the formal charges will be wonky, so it can't happen. So then we're gonna have 5 carbon, like longest carbon chain of 5. So we have 1, 2, 3, 4, 1, 2, 3, 4, 5. And then you're gonna put a carbon, chlorine here. Go into 4. 1, 2, 3, 4. Oops. Put one here. So then you're gonna have another chlorine here. And then you can also do the same thing here. You can add another chlorine here. And then another chlorine here. And also another chlorine here. So these also are your isomers. So yeah, and then also if you have 3, oh oops, I also got to include these ones also, my bad. Next is to have a 3-carbon chain, so you have 1, 2, 1, 2, 3, and then you're going to account for other 2 carbons and put your Cl group here. Now in this case, if you have something branched like this, all these methyl groups are equivalent to each other, so no matter where you put the Cl group, they'll all be equal. So this is the only isomer with a carbon chain of 3. So yeah, these are your 1, 2, 3, 4, 5, 6, 7. So there are 8 structural or / constitutional isomers. If the question asks you to find structural or constitutional isomers, then you're good. However, if they say find all isomers, you're forgetting something. You're forgetting the optical isomers. So these involve cis / trans or chiral centers. Since there's no double bond, we can ignore. So we have to find chirality centers and then antimeters. So then we can have to find the chiral centers, and they involve basically the criteria for chirality again is a carbon which has 4 distinct groups. So let's check for it. So in this carbon over here, there are 2 hydrogens. So you cannot have 4 distinct groups. Over here you have a methyl group, you have a hydrogen, you have a chlorine, and you have a propyl group. Yes, this is a chiral center and will have a mirror image or an antimirror. This one has 2 of the same ethyl groups. Nope. Over here, 2 of the same hydrogens. No. This one has a methyl group, chlorine, and then isopropyl hydrogen. Yes, this has an enantiomer, so we'll add plus En. This one has two methyl groups, no. This one over here has a hydrogen, methyl, ethyl in this group here. Yes, there has an enantiomer over here. Over here, this one has two hydrogens, no, four different groups in here. All these three methyl groups are the same. So there are 8 plus 3 equals 11 total isomers. Yeah. Okay, let's move it up a notch. Let's move it up a notch. So then let's move up. Let's make this a little harder. Yeah, let's make this a little. Okay, no. Let's make this a little harder. So we're gonna talk about C5H10. Find all of the isomers. So the first step again is to calculate DBE, which is 5 plus 1, 10 over 2, which is essentially 1. What this means is that there's either an alkene, pi bond, or a ring. So we have two possibilities for function of alkene or ring. We're trying to find both. We'll start the alkenes first. So alkene, so let's start a long chain, carbon chain of 5 atoms, carbon atoms. So 1, 2, 3, 4, 5. We can place a double bond here. 1, 2, 3, 4, 5. There's another bond here. If you were to place a double bond, let's say here or here, they will equal these molecules, because if you put a double bond here, this is just this flipped, and here this is just this flipped. So yeah, we have to ignore that. Let's take a look at 4. So if you have 4, you have 1, 2, 3, 4, 5. Oh, oops. 4, and you have to place one here. That's the only option you have. And you can place a double bond here. Oops. Place a double bond here. If you place a double bond here, it's the same thing as this molecule. Over here, if you say it's the same thing as this molecule, because like these two methyl groups are equivalent, then you can place them over here and then here also. So those are your 3 options. And then yeah, I think yeah. And then if you try to have a 3 carbon long chains, 1, 2, 3, and then count for other 2 carbons, 4 and 5. If you place a double bond here, this will violate the octet rule, because it'll have 10 electrons rather than 8, so that cannot work. So then these are your 5 constitutional isomers for alkenes. Now let's take a look at rings. Let's take a look at rings. So essentially, we can have cyclopentane. You can also have this box and then a carbon here, and then you can also have cyclopropane with 2 branches here, and then you can have 1 branch here, 1 branch here, and you can have 1 branch here, 1 branch here. So those are your 5 rings. So then we found a total of 10 constitutional / structural isomers. And now, here comes the interesting part. You have to also take into account stereoisomers. And this includes cis or trans and chiral enantiomers. So then we have to find cis and trans for alkenes. So we can find, so that means, let's find it. So this cannot have cis or trans because 2 of the hydrogens on the same side have hydrogens. This has cis or trans because the hydrogens are here. This is trans. and you can have cis also here. So that is, yeah, these two groups are pointing to each other and the hydrogens are pointing out together on the same side of a double bond. That's one. Here there's no, because there's two hydrogens over here. Here there's no, because there's two same methyl groups over here. Here there's no, because there's like two hydrogens over here. So there's one extra. Now to check for chirality in the rings, because there's no double bond. So then in each group of the cyclopropane, there's two hydrogen groups. So that means there's no four distinct groups for each carbon. So chirality is not observed here. Same thing for here in this carbon. But things get a little interesting here. Over here, you think that, over here, you wonder how to calculate, how to find if this carbon's chiral, because there's like no, it's like in a ring. Well, to calculate, why do I keep on saying calculate? Oh my god, it's like 11:30 while I'm recording this. To find if it's chiral or not, you have to see the path, the circular path this way. Back to this carbon is the same as the circular path that way. The same carbon. So when we do that, there is 1, 2, 3, 4. So there's like 3 carbons in between and nothing else. If you're going to go this way again, there's 1, 2, 3 carbons. So the path each way, like clockwise or counterclockwise, they're equal to the same carbon back. So that means we can count this as same groups. These two bonds have the same groups. So there's no chirality in them. Over here we have two methyl groups, so chirality is not observed. This one's interesting. Let's skip this one for now. Over here, same thing, right? Same pathway. Like pathway here, pathway counterclockwise is the same as the pathway clockwise. But over here, things get a little different. Let's take a closer look. So we have this compound over here, and let's take a look at this carbon. Take a look at this carbon. So this pathway, let's take a clockwise pathway. So in the clockwise pathway, you first encounter this. You first encounter this carbon, which is a methyl group attached, and this. So in the clockwise, you first encounter a tertiary carbon, so I'm going to put 3. And then the second carbon you come is secondary. So it's 2. But if you go counterclockwise, the first carbon you encounter is secondary, and the second carbon you encounter is tertiary. So these are different. These are different pathways. And thus you can say that there are two different groups. There are like two different groups. So you have a methyl group here, implied hydrogen, and different pathways. So this one is chiral. However, this group is also other chiral, because same logic as before. So there are two chiral centers or stereoisomers in this compound. And by this equation, 2n, where n is the number of stereoisomers, so 2 equals 4. However, 2 equals 4. However, if you draw them, so we're going to draw this one, we're going to draw the first stereoisomer, here, and here's right. So these are enantiomers of each other. They're two different isomers. However, these compounds have a plane of symmetry. And they are meso compounds, meaning that they do not have an enantiomer. They don't have an enantiomer because since they have a plane of symmetry, these molecules can just, they're just flipped upside down. When you flip them upside down, when you flip them upside down, you can reorient them so that the dashes can become the wedges, thus equaling this compound over here. So these compounds are essentially, what I'm saying, is the same. So there's 3 different stereoisomers for this compound. So then if we include the total isomers, so we have 10 plus 3 plus 1 over here. This is the trans. The cis. So we get 14 total isomers. That's how you get that. Alright, so let's move it up a bit. So let's talk about this one, right? Yeah. How many isomers are in C3H6O? So essentially what you need to do again is to calculate the DBE. So we got 3 plus 1, 6 over 2 equals 1. So there's either an alkene or ring. And taking a look at the oxygen atom, so there's multiple different functional groups. So pause this video and try to find the functional groups and try to find isomers on your own. Yeah, assuming you had given a go at it, so let's begin. So there could be an alcohol, there could also be an ether group, but those need to have an alkene because these groups do not have a double bond. However, there can also be a ketone, there can be an aldehyde, or there can be a what? Or there could be a ring. There can also be like a ring. There can also be a ring. So let's find out. So on alcohol, so we have alcohol with alkene. So we have a 3-carbon chain, and then we can have an alcohol in the end. We can add an alkene here, or we can also add an alkene here. And then in the middle, we can also add an alkene here. So a carbon that is directly attached to a double bond in a hydroxyl group, this compound is called an enol. This has some important implications. Keto terminization, that's some cool stuff. So you can also have ether with alkene. So you can cleave this bond a little bit. You can O group, say 1, 2, and 3. You can't put the oxygen atom in the middle of the pi bond because the pi bond will break and be disrupted because there's lack of pi overlap, and the formal charges would not be good. So we got these compounds. So then moving on, then we get let's get ketones. Ketone, the only possible way to get a ketone is over here. Aldehyde, the only way is to get over here. This as an H. And then the rings. So you can have this box, or you can have cyclopropane and then an alcohol on top. Cyclopropanol. And those are pretty much, so we have 1, 2, 3, 4, 5, 6, 7, wait, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 structural / constitutional isomers. Now let us try to find the stereoisomers. So then, the only place where it is a stereoisomer, right, if you take a look at it, I'm assuming you take a look at it, so the only place you can find stereoisomers in this compound. This one is trans, because the hydrogens are opposite of each other. So you can make them cis. So we have this, that, hydrogens are cis now. Same site, so we're including that. So in overall, there are 9 total isomers. So there we go. So now I've given you all the steps now. So I think Try doing this. Try doing this. Try to find all isomers of this. C5H12O. This one's a challenge compound. This one's a challenge compound. So like in the comments, try to give you what you think it is. It's a challenge one, good one for practice. I believe if you can get this one, you can get all those other isomer questions correct. So yeah, here it is. Here's my video. Thanks for watching and hope you learned something, and leave a like and subscribe. Thank you.